So today we are solving Leetcode problem 1438. You are given two different inputs here. So one is the nums array, which is an array of integers, and the other is the limit. So you have been asked to find out what is the subarray, longest subarray within the nums array, for which the difference between any two numbers has to be less than or equal to the limit. So first let's look at the brute force approach. So in the brute force approach, you can iterate through all the subarrays in this array in O(n) square time, and then check the constraint for each of the subarray in O(n) time. So you'll get a time complexity of O(n) cube. To look at an example, let's look at this array. So if we have to iterate through all the subarrays, we can start from this position, say as an example, and this could be one potential subarray starting from that position. This could be another potential subarray, so 10, 10, 1, 10, 1, 2, 10, 1, 2, 4, and so on till the end. So similarly, we can also find all the other subarrays starting from all the positions, as you can see here. Once we find all these subarrays, the second step would be to check whether any two elements within that subarray is less than the limit, and that is going to take O(n) of time. So if you see the total complexity, it comes to O(n) cube, as I mentioned earlier. So before we go to the better approach, I would like to point out one observation here is for a particular subarray, let's take this as an example. Now, to find out whether this subarray satisfies the constraint of the limit, all you have to do is find out the minimum element in this subarray, which is this, and find the maximum element of this subarray, which is this. And now try to find out the difference, absolute difference between this minimum and maximum, which is 10 minus 1, which is 9, and check whether 9 is smaller than the limit or not. So with that observation, I'm going to talk about the better approach that we are going to take to solve this problem, which is based on sliding window. Now, sliding window as a concept, you can see it, a sliding window has a window which has a size, and it has two parts. One is the right side of the window and the left side of the window. And at any point of time, we have the option to either increase the size of the right side of the window. That means your size of the window is going to increase if you slide the right side, or you can very well decrease the size of the window by sliding the left side of the window in this direction. So let's take a look at an example. Now, as an example, if you start with window size of 1 here, then you can increase the right side of your window and include the element 1 as a part of the window. So now you have a window with size 2 where you have two elements 10 and 1, and you can keep on doing it in a similar way, including more and more members as you go on the right. However, based on the constraints of the problem, you might have to slide the left side of the window by excluding the leftmost element in the window. So for example, in this case, you will slide this left side here and exclude 10 from the set, and then you can do the same thing by excluding 1, 2, and then finally having only one element, which is 4 in the window. So just to reiterate, we made these two observations. So first observation was we have to use a sliding window, and the second observation was at any point of time for a particular size of the window, wherever the left and right slide may be, you will have to keep track of the min and max element which fall in that particular window, so that you can check the difference between max and min and see whether it satisfies the less than or equal to limit constraint. Now let's look at the approach to solving this particular problem using the observations we have made earlier. Now we have a starting position from index 0, which is at element 10, and from here let's say our initial window of size 1 is positioned at this first starting position. Then our min will be 10 and our max is also 10. So what we'll do is we'll check the difference between these two. 10 minus 10 is 0, which is less than equal to limit, and hence we can include size 1, which is basically this window which has one element in it, as the subarray which satisfies the constraint. So this is the first subarray that we found which satisfies the constraint. Now next we will expand the right side of this window so to include more elements. So in this case we are expanding this right window side, and we are including 1 in this. So now we have 10 and 1 as a subarray, and we are checking whether this subarray satisfies that particular constraint. Now for that we'll have to update the min element. So min becomes 1 here and the max remains 10, because in this window your max is 10 and your min is 1. So we'll check again the difference, 10 and 1, it is 9. So the constraint is violated here. So there is constraint violation. So we cannot have this particular subarray satisfy the particular constraint, hence this array cannot be included. Also, one more thing I would like to mention here is not only can you not include this subarray because it violates the constraint, even if you try to expand this right side of this sliding window by including more elements, it is of no use, because these two elements are still going to violate your constraint, and hence there is no need to expand your right side. You can just stop your window right here for these two elements. Then next, there is as you cannot expand your right side of the window, you have to shrink your left window so that you can exclude the element, the first element on the left, and see whether the remaining elements, which is 1 in this case, can satisfy the constraint. So just to reiterate again, we identified that these two cannot satisfy the constraint, and we also know that we cannot expand the right window, and hence we have to shrink the left window and exclude 10 and check whether the remaining elements within this, in this case it is only 1 element, does satisfy the constraint or not. So for this, what we'll have to do is, because we are shrinking the window on the left, we will have to exclude 10 from this 2 variable wherever it is present. So in this case, let's say 10 is falling out of the window, so we'll have to make sure it goes out, and now your min is always going to be 1 because 1 was your min, and now your max also becomes 1. So in this case, both your min and max are 1, and we are kind of similar to where we started, where we had 10 and 10. Here we have 1 and 1 for this window, and we'll check whether this constraint is satisfied. So in this case, 1 minus 1 is 0, which is less than your limit, and hence we can include this subarray as a part of the solution. Now from here, we were here earlier, now we'll try to again expand the right side of the window and see whether the constraint is violated or not. So we are including 2 in the subarray, so we have 1 and 2. So now your min is 1 and your max becomes 2. So you check whether 2 minus 1 is less than equal to limit. It is. So now we can again proceed further. We can expand this window further on the right, and now you have 1, 2 and 4. We'll check in this case your max is going to become 4. Your min is still going to be 1. You'll check whether 4 minus 1 is less than the limit. It is. So again you can safely expand your window. So in this case, now your rightmost part of the sliding window is going to be 7. So you'll exclude, you will remove this and make this as 7. So now you will check the constraint. So min is again 1. So we are looking at this array here, subarray here. So 7 minus 1 is 6, which is greater than 4. Now this violates the constraint. So you cannot have this subarray as a part of your solution. You cannot consider that. And now you can start shrinking from the left. So if you notice, we started from here, we went all the way to here, here and here. We found that the constraint was violated here, and hence there was no point in going any further on the right. So we stopped here, and now we start shrinking the left side to check the new subarrays. So now let's try to shrink this window to this. So we have excluded 1. So let's exclude 1. So what we have to do is we have to update min to 2. So in this case the window size is this, and your max is 7 and min is 2. So again you can check 7 minus 2, it's 5. So it again violates your constraint. So you have to basically again do a shrink. So exclude this from here, have 4, and your 7 minus 4 is less than equal to your limit. So you can have this as a possible subarray. Now you can now start again expanding on the right. So let's include 2 as a part of this subarray. Now you have 4, 7 and 2 as your subarray that we are looking at. So the new element 2 is smaller than 4, so this becomes 2. Now you check the constraint 7 minus 2, which is 5, so which again violates your constraint. So you cannot have this subarray because it is violating the constraint as a part of your solution. So you again have to shrink from your left. So that means you have to exclude 4, but 4 was never having any impact. So basically now you will again look at 7 and 2. Again we are in the same situation because nothing changes here, and this also violates the constraint. And finally you come here, and there is only one element, which is your 2 element, which is 2 minus 2 is 0, which is less than your limit, and that can be part of your solution. But usually you will kind of stop here because there is no point in shrinking this, because the maximum size, this maximum size is always greater than any size which is less than this, just as an extra observation. Again, to summarize and reiterate, you will start with a window size of 1, then you will expand your window size. You will check whether the constraint is violated or not. In case the constraint is not violated, you are going to keep on expanding your right side. The moment your constraint gets violated, you stop expanding the right side and you shrink the left. In the process of shrinking the left, you have to take care of updating your min and max values by looking at what went out of the window on the left. So that is an important piece that you need to take care of. Even when you expand your window on the right, you need to make sure that your min and max are updated accordingly to reflect and see whether the newly included element on the right has any impact on min and max. Now let's look at the thought process behind choosing what data structure to use to represent this min and max. For that, let's look at this particular example for now, and let's ignore this limit constraint for now. So let's start, for this example we have to start with window size 1, so first element is 1, and the constraint, assume that the constraint is satisfied. So you are going to expand your right side. So here what is going to happen is now your min is going to be 1 and your max is going to be 10, and again assume that the constraint is satisfied. So let's say you expand your right side again. Now your min remains 1 and max also remains 10, so including 2 does not impact your min and max. So now again, let's say we increase the window size on the right. Here what is going to happen is including 20 is going to impact your max. So your max is going to become 20. Your min remains the same, which is 1 in this case. So in this subarray, your max is 20 and the min is 1. Now let's assume that the constraint gets violated for this length. So what you're going to do is you have to shrink the window from the left, which I had mentioned earlier. So when we shrink the window from the left, we have to exclude 1 here. And now the question arises at this point of time is, your min was 1 and your max was 20 for this window. You shrank the window from the left and you excluded 1. So now your min is getting impacted. So you need to find the new min which is present in this window. So how would you do that? So one way to do that is probably you'll have to go through this entire array. It may not be only 3 length, it may be a big array. In which case, whenever you shrink, you might have to go through this entire remaining array to find out which is the next minimum. So remember, after 1, the next minimum among these 3 is 2. So this is the remaining, or the next bigger element after 1. So to find that out, you might have to iterate through this entire array and find which is the next. number which becomes the minimum, right? So this is basically the crux of the problem, and this is going to drive the decision with respect to the data structure that you are going to choose to represent this kind of data for min and max. So again, to reiterate, let's say here if we found the minimum, which was 1 in this case, if we had to shrink the window from the left, then we have to make sure that we exclude this element that has fallen out of the window from the left, and we'll have to figure out which is the next best number to choose for the minimum. Similarly, every time you shrink from the left, you'll have to basically make that decision with respect to what is the best next number to choose based on what value has fallen out of the window. And to precisely have that capability, if you look at a data structure which is called array_dq, we can basically use this array_dq data structure to represent this kind of pattern in a very efficient way. So in this specific example, we have to represent the min using array_dq data structure, and the way we can represent that is, let's say when the window size is 1, we have 1 as the first element of the 1 as the only element of the array_dq. When we increase the size of the window, we might have to add 10 at the end, so we have 2 elements in an increasing order. So this is from lowest number to going towards the highest number. When let's say we further increase the window on the right, we have to, as I said earlier, we have to choose the next number which is bigger than the minimum. In this case it is 2. So what we can do is we can get rid of 10 and just have 2 after 1 in this data structure. Now let's say if we increase it further, then we get 20 here, and let's say if we if none of the constraints are violated, assuming none of the constraints are violated, if we increase it further, then again, because we don't require 20 here, we can get rid of 20 and we can have 3. So if none of the constraints were violated and we continuously increase the window size, in this case on the right, then you would have in your minimum array_dq, you will have 1 followed by 2 followed by 3 as your numbers. And why this becomes important is, now assume that you have this in your minimum increasing array_dq, you have this maximum subarray, and now you are trying to shrink from the left, right? This is just for demonstration purpose. It is not relevant to actual problem, but I'm just trying to expose the thought process behind choosing array_dq as a data structure. So let's say if you use this and now you shrink from left, then 1 is going to fall behind. So what you can do, fall out from the left side. So what you can do is you can get rid of 1, which is array_dq allows you to delete elements from the front as well as from the back in constant time. So when you shrink the window, you can check whether 1 is here on the left side and just drop it off. Here now what is going to happen is you have shrank the window. Now among this, your next best number is 2, which is at the front of the queue here, and you still can get that in constant time. And even if you shrink in this case, this is not going to have any impact because we have already removed 10 from here. So now let's say our window size is 3, so our minimum element is 2, as you can see here. And if we continue to do that, if we continue to shrink from the left, if we have only this 2 element, 2 is falling out, so we can just get rid of this in constant time from the front of the queue. Now among this, the remaining element in the queue is 3. So you hopefully can understand why we have decided to use array_dq as a data structure to represent the min and max in this case, to efficiently find which is the next best number to choose from for the min and max. So now finally we are going to look at solving this particular problem with the constraint based on what we have learned so far. So initially we are going to have a window size of 1 and starting position of 0. So we'll include 10, and our array_dq, both the array_dqs will have the number 10 and 10. So the min DQ, as I said earlier, will have elements in increasing order, whereas max will have elements in the decreasing order. So in this case 10 minus 10 is 0, which is less than the limit, so the constraint is satisfied. So we can safely increase the size of the window. So when we increase the size of the window, we have one value here. So since this is increasing DQ, we have to make sure that 1 becomes the first element in this increasing DQ. So we have to delete 10 and have 1 here. 10 remains the same, but we have to append 1 in this case to this decreasing DQ. Now here we are going to check the first element of both the queues, 1 and 10, and find out the difference between them, which is 9. But 9 is not less than 4, so the constraint is violated for this. And for that reason we have to shrink the left of the window, and when we shrink the left of the window we have to get rid of 10. So 10 is in the front of the array, so you'll have to, whenever you shrink the window, you have to check whether this element is present at the front of min or max queue, and wherever you find it you have to remove that in constant time. So here in this case 10 is at the beginning of this, so we just delete it in constant time. Now again our window is here, so we now again start shrinking the right of the window. So in this case we found 2, so we can include 2 here safely, and in this case we can get rid of 1 and have 2 at the beginning of the array. So we have again in this 2 at the end of this iteration here we'll have 1 and 2, which is 1 and 2, 1 being minimum, 2 being maximum. We again find the difference, we find that it satisfies the constraint, and then now we have to increase the right side of the window. So here we have found 4. Now 4 when it comes to minimum again is you can append it here, whereas here 4 is greater than 2, so you have to get rid of all the elements which are lower than 4 in this case. So I'll delete 2 and you have 4. Again you have in this you have 1 and 4, 1 and 4, 1 being minimum, 4 being maximum. Try to find out the constraint, whether it satisfies the constraint. It does satisfy the constraint. So again you expand the right side. So you have to include 7 here. So let me include 7 here, and since 7 is greater than 4 in this case, I have to delete 4 and have 7. So in this case again 1 and 7, let's check that. So this violates the constraint. So 7 minus 1, 6 is not less than 4. So what we have to do is, in this case we'll have to shrink the left side. So when we are shrinking the left side, we'll have to check the first element, in this case 1 and 7, and 1, since 1 is falling out of the window when we slide this, we have to delete 1. Now we are looking at this place. Now again we'll check whether 7 and 2, which is 7 and 2, the difference between these two is satisfying the constraint. It's not satisfying the constraint, and hence we can get rid of the left side. So we shrink the window again. So again we delete this 2. So you have 4 and 7. For this you have 4 and 7. So in this case 7 minus 4 satisfies the constraint, which is less than 3. So we can less than 4, sorry. So we can increase the size of the right side of the window. So in this case what is going to happen is, now since this is increasing, we have to delete, so 2 needs to be added here, but for it to be added here we have to delete the elements which are bigger than 2. So 7 got deleted and 4 gets deleted. You have 2 at the beginning, or the first element of the min increasing queue, and here you can safely add 2 at the end, and now you have 7 and 2. So 7 minus 2 basically again does not satisfy the constraint. So you can shrink the window again further, and for that you have to get rid of this, and finally you have 2 and 2. So in this case 2 minus 2 is 0, which satisfies the constraint. So this is one of the possible subarray. So this is basically the reasoning or logic that is used to identify what data structure is to use, what is the logic that is to be used to solve this particular problem. So as you have seen, there are few things that are very important for this problem. First is you need to use a sliding window in order to solve this problem efficiently. Second is you need to maintain min and max. And third thing is, for maintaining min and max, the efficient data structure to choose is array deque. So if you understand these three parts, then it will be easier for you to solve this problem for any interview. Also, finally, the source code for this, I've pasted a link below this video, and I will not be going into the details of the source code because the source code is pretty self-explanatory based on what we have discussed in this video.